Good morning, everyone. Let's wait a few moments so everybody comes in. Questions while we are waiting? If you want me to go over an example, give me one, we can do that. The web work will be released through CrowdMark So I think we agreed on tomorrow morning, 9 a.m. So at that time, you'll receive an email from CrowdMark directing you to the midterm. Once there, so the midterm, I finally got around to writing it. It's 6 questions. 2 questions are worth 5 marks. 4 questions are worth 10 marks. And on each question, you'll do the work on paper, and then you'll upload. You'll take a picture, and you'll upload in the space provided. You can remove pages, change them as you wish throughout the entire 72 hours. What you need to do before the 72 hours is up, though, is to submit your work. There's a button you can click to submit. That needs to be done before the 72 hours is up. So we're looking at the square root of 3 plus I. Let's do it. How rigorous do you have to be on the exam? In some cases, not rigorous at all. You'll see there are different types of questions. Some are very easy, very straightforward. Others are more tricky. Yeah, so I mean, it's going to depend on the question. I will allow you to work on iPad and upload it through screen capture. That'll be fine. Yeah, my mistake, right? Last time I said the midterm was on Friday, but I was confused there because I am teaching 3 courses, and another course is being released on Friday, but ours is actually tomorrow. Ours is being released tomorrow, 9 a.m. So, and you've got 72 hours. That's what we had agreed upon. So my mistake for the confusion, it's tomorrow. Square root of 3 plus I, right? I mean, the question, the obvious question is this a complex number? That's the question that arose naturally. So And by the fundamental theorem of algebra, the answer is yes. This has to be a complex number. So in that case, it has to be, we have to be able to rewrite it in the form a plus ib. Where a and b are real numbers. So if we square both sides, if you do the same to both sides, equality is maintained. What happens if we square both sides? If we square both sides, left-hand side becomes 3 plus I. Right-hand side, a squared. This times 2. So I 2ab. And then plus this square. But of course you know I squared is -1. So this is a squared minus b squared plus I 2ab. And this is equal to the left-hand side. And is asking about I to the 89. I'm going to let you think about that. I'm going to let you think about that. Figure out, so you're looking for I to the 89. Well, try to see a pattern. What is I squared? What is I cubed? What is I to the 4? And so on and so on. Until you see a pattern arising, which I'm sure you'll see immediately. So we have this. If you take the real part of both sides, again, equality is maintained. But the real part of the left-hand side is 3. The real part of the right-hand side, a squared minus b squared. And instead of taking the real part, if you took the imaginary part instead, imaginary part of the left is 1. Imaginary part of the right, 2ab. So you have 2 equations, 2 unknowns. You can solve however you wish to. In particular, from this one, you can solve for b. b is equal to 1 over 2a. And if you plug that back into this one, what do we get? b is 1 over 2a. So we have this. Square that. So what do we say? 3 is equal to a squared minus 1 over 4a squared. Again, you have options here. Maybe common denominator or multiplying both sides by 4a squared. Again, if you do the same to both sides, equality is maintained. So let's do that. Here we get 12a squared. 4a squared times a squared is 4a to the 4. And here, 4a squared times 1 over 4a squared. Well, everything cancels, and we just get 1. Multiplying by 4a squared gets rid of the denominators. bring this to the other side. And here, you're thinking to yourself, this is a polynomial degree 4, but you only have a to the 4 and a squared. It's really a polynomial of degree 2 in a squared. So in other words, if you let x be a squared, this becomes 4x squared minus 12x minus 1. It's a quadratic in a squared. You can try to factor that. If you can, you're good to go. If you cannot, since it's a quadratic, you can always use the quadratic formula. So using the quadratic formula, negative b plus or minus square root of b squared minus 4ac all over 2a So this 144, which is 12 times 12, is really 4 times 3 times 4 times 3. And here this is 16, so 16 times 9. And you can factor out a 16. Right? Square root of 16 is going to be 4. And then you get 9 plus 1 is 10. And if we factor out a 4 from the top, 3 plus or minus root 10 over 2. This is your x, or a squared. But root of 10 is bigger than 3, right? Because root of 9 is 3. So root of 10 is bigger than 3, and 3 minus something bigger than 3 is going to be negative. So it cannot be equal to a square. So we must use the positive square root So a squared is the positive square root, 3 plus root 10 over 2. And a is the square root of that, plus or minus. So if b is 1 over 2a, you have the two roots. If a is the positive square root, then b is going to be the positive there as well. So if you take the positive square root, you get this. Or if you take the negative square root, then it's negative for both. there it is. A very nice midterm type of question. And somebody was asking about how rigorous you need to be. Well, I mean, let me say this. You need to show all your work. All the work needs to be shown. So everything we did here, this was a question on the midterm, you'd have to show all of this. Let's look at Anna's question for a moment. Anna had a polynomial which she wanted to factor. Minus 2x to the 4 plus x cubed minus x squared plus 4x. First of all, it's a polynomial of degree 4, so you know it's reducible. Immediately, without doing any work, there's an x everywhere. So you can factor out an x. So that was easy. Now what you have in the brackets is a polynomial of degree 3. And as I suggested, there is a cubic equation, very much like the quadratic equation, which will give you the actual roots. I don't expect you to know it by heart. You can look it up if you want. I mean, I don't expect you to use it on, well, in fact, I don't want you to use it on the midterm. So what are we going to do here? Well, we're going to search for a root. This is the method that we saw in class. Can we spot a root? I mean, we almost had one. If this was negative, then you'd have minus 2. If x is 1, you'd have minus 2, minus 1, minus 1. Would have been minus 4 plus 4. This would have been 0. So that would have been nice. It isn't. So we can't just change it. If x is 2, this is 8. So minus 16 plus 4 plus 2 plus 4. Yeah, so that doesn't work. Well, I think we don't have much luck. Yeah. So as far as we're concerned, we don't have the tools sufficient to factor this. Is minus 1 a root? Yeah, no. So we don't have the tools to factor this. We know it has to factor, but yeah, so that's where we would stop. That's where our knowledge for this course stops. But one thing we do know for sure, though, we do know that it is reducible. It's just that we cannot factor it. How are we doing here? Questions? I was going to put a question on total order. Then I decided not to. I'll tell you what my question was related to this, let's say. I would have asked you, would it make sense to ask for the positive square root versus the negative square root of 3 plus I, say? And as you know, the answer is no. This question doesn't make sense because the complex numbers are not totally ordered. Factoring irreducible, well, as you know, you cannot factor irreducible polynomials. So I'm sure you meant factoring a polynomial into irreducible factors. If you have a question, we can do it. Otherwise, we'll move on. My question regarding total order, right? In this question here that we were answering, we were looking for the square root of 3 plus I. A question on the midterm that almost came up was, does it make sense to ask for the positive square root of 3 plus I versus the negative square root of 3 plus I? And as you know, that question doesn't make sense because the complex numbers are not totally ordered. Questions? David, are you coming up with a polynomial there, or are we moving on? Let's move on. And we can always answer your question. We're going to have a short class today, so we can answer some questions at the end if you want. We were discussing series on Monday. Recall that a series is an infinite sum, right? We are adding infinitely many numbers together. And we saw a nice trick to help us evaluate series. And let's remind ourselves using an example. First, let's remind ourselves what this really means, right? This is known as the sigma notation. The Greek sigma here meaning sum. We are summing, we are adding all of the expressions for n from 1 to infinity. So when n is 1, we get 1 over 4. Plus when n is 2, we get 1 over 4 squared. Plus when n is 3, 1 over 4 cubed, and so on, right? Plus because of the sigma. It's the sigma that gives us the plus here. Right? Or if you prefer, 1 over 4 plus 1 over 16 plus 1 over 64, and so on, and so on. We saw that this converges, right? This is part of a bigger family of series known as geometric series. But if you missed it, or if you forgot how that works out, let's remind ourselves with this example, right? Let's call S this sum, 1 over 4, 1 over 4 squared, 1 over 4 cubed, and so on and so on. And we're going to multiply S by a good value so that when we subtract the two, a lot of stuff cancels out. Right? Observe what happens if you multiply S by 1/4. So multiply every element by 1/4. What do we get? 1/4 times 1/4 is 1/4 squared. 1/4 times 1 over 4 squared is 1 over 4 cubed. and so on and so on. And when we subtract the two, s minus 1 over 4s, right? So this minus this minus this, these two cancel out. This minus that. Those cancel out. Everything cancels out. Sorry. Except the first term. Now, s minus a quarter s. If you have something and you take away a quarter of it, you're left with 3/4. So 3/4 s is equal to 1/4. If you multiply both sides by 4 over 3, or divide this by 4 over 3, whatever, you see that s is equal to 1/3. So the sum of all of these numbers is 1/3, or that series converges to 1/3. And this idea can be extended as we did, right? We extended this to this family, right? This is 1/4 to the n. We generalized to a to the n as long as a was between -1 and 1. As long as a was a fraction, this whole process repeated itself in exactly the same way. And we gave this family a name. These are known as geometric series. This geometric series converges to 1 over 1 minus a as long as a is in this interval. And we needed the fact that this was a fraction in order for the terms to get smaller and smaller, ever closer to 0. And this gave rise to the divergence test, which tells us that if the terms aren't going to 0, then the series does not converge, or the series diverges. Right, so we saw the divergence test. Which tells us that if the terms are not going to 0, the whole series diverges. Let's take an example. Consider the series n plus 1 over n. Let's write out the first few terms to get an understanding of what's happening. Right, this is 2 over 1. When n is 1, plus when n is 2, this is 3 over 2. Plus when n is 3, this is 4 over 3, and a 5 over 4, and so on and so on. It's easy to see that the term n plus 1 over n, if you break that up into two pieces, this is n over n plus 1 over n, or 1 plus 1 over n. And since we are restricting our attention to natural numbers here, this is bigger than 0. So this whole thing is bigger than or equal to 1. Each of the terms are going to be bigger than or equal to 1. So this is going to be bigger than or equal to 1 plus 1 plus 1 plus 1, and so on. If you're adding 1 infinitely many times, of course, you're going to get infinity. So this series must be infinity. This series diverges. And that happens because the terms are not getting closer and closer to zero. Right? But in the geometric series, if you are restricting your attention to a fraction, then you're fine. You're fine. Everything works as it should. I left you with the observation that if we replace A with X, what do we get? We get that the function 1 over 1 minus X is equal to this business, X to the n. And this is true for any X between -1 and 1. Right? This, what is this? This is 1 plus X squared plus X cubed plus X to the 4. Right? When n is 0, you get some X to the 0. Plus when n is 1, plus when n is 2, and so on. So this right-hand side can be thought of as an infinite polynomial. And you have that this function is equal to this infinite polynomial. The question arises naturally, are there other functions which have a similar relationship? Indeed there are. In particular, sine x has this nice representation, -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Right? So when n is 0, first of all, for those of you unfamiliar with factorials, and factorial is the product of all the numbers from 1 to n. So 5 factorial is 1 times 2 times 3 times 4 times 5. So here, let's write out the first few terms. When n is 0, minus 1 to the 0 is 1. X to the 1 over 1 factorial, so that's just 1. So just x. Plus, when n is 1, you get a minus 1 to the 1, which is minus 1. X cubed over 3 factorial plus, when n is 2, minus 1 squared is 1. X to the 5 over 5 factorial, and so on and so on. 3 factorial is 1 times 2 times 3, so that's just 6. 5 factorial is 1 times 2 times 3 times 4 times 5. So you can work that out. What is that? This is 6 times 4 is 24 times 5 is 120. And so on and so on. So you have this nice infinite polynomial that is equal to sine x. And in fact, this is exactly how your calculator deals with sine. When you plug in sine of 1 into your calculator, how does your calculator calculate what sine of 1 actually is? Well, it plugs in x equals 1 into this thing. Right? So sine of 1 is going to be 1 minus 1 over 6 plus 1 over 120, and so on and so on. And what it does is it approximates this infinite sum to within 8 decimal places. Your calculator only has 8 decimal places, so as long as the approximation is good enough, then that's the answer it spits back. So this stuff, rewriting a function as an infinite polynomial, is known as Taylor series. And as we may have convinced you, it has immediate applications to calculators and computers. That's how we can deal with the sine function in a relatively simple way. You usually see this in Cal 2 or Cal 3. It's great stuff. But for now, let's go back to the idea of telescoping sums that we encountered in the geometric series. And let's observe that it also comes up naturally in other situations. Consider the following series. What is that? Well, when n is 1, you get 1/2. Plus, when n is 2, 2 squared is 4, plus 2 is 6, 1 over 6. Plus, when n is 3, 9 plus 3 is 12, 1 over 12, and so on and so on. It's not clear that you can multiply this by any good number and things will cancel. And in fact, it's not possible because this is not a geometric series. It's not a number to the power n. However, observe that 1 over n squared plus n, which is really n times n plus 1, you can break this up as 1 over n minus 1 over n plus 1. Let's convince ourselves. If you were to put everything back over a common denominator, you would get an n plus 1 minus n. The n's cancel, and you're back to your 1 over n times n plus 1. Of course, the obvious question arises, how did we know to do this? How are we able to do this? It's not something I want to get into. And it's not something I'm going to assume you can do on the final exam, but let's just go with it. Because I'm sure you are convinced that this is the same as that. So if we are looking at this series, we can instead just consider this series. They're the same series. And what is that? When n is 1, This is 1 minus 1/2. Plus, when n is 2, 1/2 minus 1/3. Plus, when n is 3, 1/3 minus 1/4. And so on and so on. And you see what's happening, right? The 1/2s cancel out nicely. The 1/3s cancel out nicely. The next term would be when n is 4, and you'd start with a 1/4, which would cancel with this one. Everything cancels except 1. So you have this telescoping sum idea coming back in a different scenario. How are we doing here? Questions? Anybody? We mentioned the divergence test last time. We mentioned it again today. What does the divergence test say? Change that. If the terms of a series are not getting closer and closer to 0, the series diverges. So if the terms of a series are not getting closer and closer to 0, the series diverges. It's easy to read too much into that. It's called the divergence test because all it gives you is divergence. It never gives you convergence. What I mean by that is, even if the terms of a series are getting closer and closer to 0, that does not guarantee that the series converges. Example, the series 1 over n diverges. Let's prove that. First of all, what is this? This is the series. When n is 1, you get 1. Plus when n is 2, you get 1/2. When n is 3, you get 1 over 3. Plus 1 over 4, 1 over 5, and so on. You see that the terms are getting smaller and smaller, right? You have a fraction with 1 over a number that is getting larger and larger. So when n is 1,000,000, you have 1 over 1,000,000, very small number, and they get smaller and smaller. However, when you add all of these numbers up, you still get infinity. The series diverges. Why is that? Let's prove it. Well, I probably have enough room over there to prove it. Right, let's write a few more of the terms. 1 over 5, 1 over 6, 1 over 7, 1 over 8. And then you'll have 1 over 9, all the way to 1 over 16. and then 1 over 17, and so on, right? We're just going to group them. I'll group the 1 over 3 and 1 over 4 together. And I'll group the 1 over 5 all the way to 1 over 8 together. And the 1 over 9 all the way to 1 over 16 together. And then it would have been the 1 over 17 to 1 over 32, and so on and so on. And I'm going to make everything smaller by replacing the terms in the brackets by the smaller of all the terms. So which is smallest between 1 over 3 and 1 over 4? Of course, you know that it's 1 over 4. So I'm going to replace this 1 over 3 by a 1 over 4. I'm therefore making everything smaller. This is bigger than this. In the next bracket, 1 over 5, 1 over 6, 1 over 7, 1 over 8, which term is the smallest? You know what it is. It's the one with the biggest denominator. This is the smallest of the terms. So I'm going to replace all of those by 1 over 8. I'm making, again, everything smaller. In the next group, which is smallest between 1 over 9, 1 over 10, 1 over 11, 1 over 12, 1 over 13, 1 over 14, 1 over 15, 1 over 16. Of course, you know it's the last one, the one with the largest denominator. So I'm going to replace all of them with 1 over 16. In the next group, I would have grouped 1 over 17 all the way to 1 over 32. And if you want to replace those with the smallest is 1 over 32. So 1 over 32, all the way to 1 over 32, and so on and so on. 1 over 4 plus 1 over 4, what is that? Right, this term in the first brackets, 1 over 4 plus 1 over 4, that's 1/2. What about the next bracket? You have 4 of the 1 over 8s. So 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8, that's 4 over 8, which is 1/2 again. And here, how many of the 1 over 16s do you have? Well, you have from 9, 10, 11, 12, 13, 14, 15, 16. You have 8 of the 1 over 16s. Or 1 over 2 again. And in here, you'll have 16 of the 1 over 32s. So 1 over 2 again. And so on and so on. 1 over 2 for all the brackets. So this is like adding 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2 forever. And you know what's going to happen then, right? You're going to get infinity. So this sum is bigger than or equal to infinity. It has to be infinity. The series must diverge. How are we doing? Why can't we do this with every series, right? I mean, it seems that you could extend that, but in a lot of the other series, the terms are getting smaller and smaller faster. So whether a series converges or diverges is really a measure of how fast the terms are going to zero. If they don't go to zero fast enough, the series diverges. If they go to zero fast enough, the series converges. In the geometric series, these were going to zero fast enough. You couldn't do this grouping idea. It just doesn't work. It's impossible to do that. Here, 1 over n, even though 1 over n does go to zero, it doesn't go to zero fast enough. This series 1 over n is part of a large family of series, right? Where you have the series 1 over n squared, which is 1 plus 1 over 2 squared, plus 1 over 3 squared, and so on, right? Or 1 plus 1 over 4 plus 1 over 9. And the series 1 over n cubed, which has a similar expansion, and so on. In general, you have this family 1 over n to the p, which is known as p series. This family is closely related to the Riemann zeta function, very important family of series. And these converge if p is bigger than 1 and diverge otherwise. In fact, not only do they converge for p bigger than 1, but we know what a lot of them converge to. The series 1 over n squared, right, which is 1 plus 1/4 plus 1 over 9. That's when n is 3, when n is 40, and 1 over 16, 1 over 25, and so on. We can show that this converges to pi squared over 6. So not only does it converge, we know what it converges to. The series 1 over n to the 1 over n to the 4, which is 1 plus 1n is 2. That's 1 over 16. When n is 3, that's 1 over 81, and so on. We can show that this converges to pi to the 4 over 90. In fact, we know what this series converges to if p is an even number. We can work that out. Interestingly enough, though, nobody knows what 1 over n cubed converges to. 1 over n cubed, which is 1 plus 1 over 8 plus 1 over 27, and so on. Nobody has shown what this converges to. It's still an open problem. We know it converges. We can prove it converges, but we don't know what it converges to. So once you've finished the midterm over the weekend, you can try your hand at figuring out what this converges to. Fame and fortune await, if you can work that out. Questions? Anybody? How are we doing with the material? Was it David that was going to ask me a question, or am I just making that up? Any questions about midterm material? It was David. Very good. How are we doing with this series? Any questions on series? CrowdMark will send you an email to your McGill email, and you can just follow the link. Euler number? The definition of a geometric series is a series that has this form. Well, it doesn't matter where you start actually, but a series that has this form. So a number to the power n. So in particular, 1/2 to the n, or 1/2n. Right, this is a number to the power n. This is a geometric series. This is not a geometric series, right? You cannot write this as a number to the power n. So the Euler function, phi n, is the number of elements, 1, 2, 3, all the way to n minus 1, which are relatively prime to n. Let's take an example. Let's look at phi of 8. What is phi of 8? Well, what are the numbers less than 8? So you have 1, 2, 3, 4, 5, 6, 7. Which of these numbers are relatively prime to 8? That's the question. What does relatively prime even mean? We gave a definition of relatively prime, right? Elements A and B are relatively prime if what? It's a good midterm question. This could come up on the midterm. What does it mean to be relatively prime? Does anybody know? Anyway. The GCD is 1. Thank you, Lilia. GCD is 1. So let's ask the question. What is the GCD of 1 and 8? Well, that's easily seen to be 1, right? The only number that divides 1 is 1. So the GCD has to divide both 1 and 8. That's equal to 1. So 1 is relatively prime to 8. What about the GCD of 2 and 8? What is the largest number that divides both 2 and 8? Certainly 1 does, but 2 does as well. Thank you. So 2 is not relatively prime to 8. And you keep going. Is 3 relatively prime? What is the largest number that divides 3 and 8? Easily seen to be 1. What about 4? 4 and 8. Largest number that divides 4 and 8 is 4. 4 is not relatively prime. Largest number that divides 5 and 8? That's easy to see. That's 1. Largest number that divides 6 and 8? 2 divides 6 and 2 divides 8. So 6 is not relatively prime to 8. And largest number that divides 7 and 8 is 1 again. These are relatively prime. How many numbers less than 8 are relatively prime? 1, 2, 3, 4. 5 of 8 is 4. A lot of people mistook that to mean prime numbers less than 8, but that's not what it means. It's numbers that are relatively prime to 8. Questions? Anybody? Are we doing? Everything good? No other questions on material or anything? We're good to go? Thank you all for coming. Like I said, you should get an email from Crowdmark tomorrow, 9 a.m. If you do not, for whatever reason, give it a few minutes, of course. But if by 9:15 you have not gotten an email, or if you wake up later than that and no email has come to you, please email me. I will fix whatever issue there is. Like I said, you'll get an email from Crowdmark and you can just follow the link to the exam. If you have questions, please email me. I ask that you not discuss the exam with anybody else, students, TAs, friends, professors. This should be just your work. You are allowed to use the internet, whatever you want to use, but don't ask for help on forums. Don't post anything on forums. That's the same as talking to other people. So no communication as far as the midterm is concerned. Individual work, but you can use the full power of the internet except for forums. I will ask that you show all your work though, unless it's specified that you don't need to. Thank you all for coming. Have a good midterm and a good weekend. I will see you on Monday.